In 1978, computers could only do one thing at a time. Today, they manage millions of tasks silently, instantly, and intelligently. In the same year, Apple would release its first operating system called Apple DOS, developed for the Apple II series. Apple DOS was created by Paul Lawton, Randy Wigginton, and Steve Wozniak, written in 6502 assembly. It was a massive technological leap forward, enabling the Apple II to manage disk storage. Now let's see its modern counterpart. This macOS, the difference does not only lie with the cosmetics, but also with its architecture and engineering. It is the result of over 4 decades of evolution that all started with the Apple DOS. In this video, we'll compare old and modern operating systems across 3 core foundations: CPU scheduling, memory management, and process handling. Let's rewind 4 decades and see how far computing has come. This is the story of how operating systems evolved, from Apple DOS to macOS, not just in appearance, but in how they think.
First things first, let's talk about the 2 operating system CPU scheduling. CPU scheduling is the process by which an operating system decides which program or process should use the CPU when multiple tasks are available. Apple DOS followed a single tasking model. With the limited memory and processing power of the Apple II, CPU scheduling was mostly unnecessary. The CPU became fully controlled by program which executed their instructions until they reach completion or until they choose to release control back to the operating system. The operating system Apple DOS lacked support for multitasking, time slicing, priority levels, and preemption. The system functioned without process tables and ready queues and interrupt-driven context switching mechanisms. At this stage of computing, the simplicity was a necessity. On the other hand, macOS used the hybrid XNU kernel, uniting Mac kernel scheduling with Berkeley Software Distribution Process Management or BSD. The system design allows Mac OS to perform preemptive and priority-based scheduling since the operating system controls CPU execution and interrupts active operation to execute those with higher priority or urgency. The new operating system Mac OS includes quality of service, which enables applications to share their task priority with the scheduler. This determines CPU priority execution timing and resource allocation. The system also uses Grand Central Dispatch or GCD to work with the scheduler for managing concurrent tasks and CPU core workload distribution across performance and efficiency core on Apple Silicon, guaranteeing peak system performance and power efficiency. Now that switching task has been addressed, this approach dedicated the next challenge: memory management.
In terms of memory management, Apple DOS only operated an environment with extremely limited memory, often as low as 64 KB of RAM. The disk operating system itself used about 12 to 14 KB of memory, leaving only 50 KB for programs to use. Memory management in Apple DOS was very basic and mostly manual. Programs were loaded into a fixed memory location and had unrestricted access to all memory. There was no protection, allowing for programs to read or overwrite any part of the memory addresses, including the operating system itself. Apple attempted to improve memory handling with the classic Mac OS, introducing system heap for the OS stops and important programs, and application heap for the user's program. But even though this OS is better than the Apple DOS, both of them still have no true memory protection, meaning users' program could mess with each other's memory, or they could read or write anywhere in the memory addresses, and a single faulty program could corrupt the entire system memory and crash the entire machine. Modern macOS solved these problems at the root. The new macOS uses a fundamentally different approach of memory management. macOS uses the XNU kernel and relies on the kernel's virtual memory system to give each process its own protected virtual address space. which means application or user programs can no longer see the physical memory directly. Instead, the virtual addresses are translated by the MMU into the physical memory. The kernel itself also uses a separate kernel allocator or zone in its own address space, preventing application from accessing each other's memory or the kernel's memory, while still sitting on top of the same paging infrastructure. This modern approach fundamentally resolved the core weaknesses of the old systems, where Apple DOS was severely limited to fixed memory addresses. With the problem resolved, macOS could finally support what early systems never could: multitasking and controlled process execution.
Now, last but not the least, process handling. Process handling refers to how an operating system creates, manages, and terminates running programs. In Apple DOS, process handling was extremely simple. The system was single tasking, meaning only one program could run at a time. There were no background processes, no process isolation, and no formal process lifecycle. If a program ended or crash control returned to the OS, often requiring a system reboot. In contrast, macOS treats everything as a process, each running in its own protected environment managed by the kernel. Processes are created using fork and exec mechanisms inherited from BSD and are monitored throughout their entire life cycle. If one process crashes, it is isolated and does not affect the rest of the system. macOS also supports multi-threading, background services, and system daemons, allowing multiple applications to run smoothly at the same time, something unimaginable during the Apple DOS era. In conclusion, Apple DOS and macOS represent two very different eras of operating system design. Apple DOS was simple and single-tasking, with no CPU scheduling, memory protection, or true process management, because early hardware could not support it. So macOS, on the other hand, is a modern operating system built on the XNU kernel, supporting preemptive multitasking, virtual memory, protected processes, and intelligent CPU scheduling optimized for performance and energy efficiency. So this evolution shows how operating systems shifted from handling full control to one program to intelligently managing many processes at once, resulting in greater stability, security, and performance. Thank you for watching, and we hope this discussion helped you better understand how operating systems have progressed from the past to the present.